Well, hi everyone, and welcome to all the participants to this session on hierarchical forecasting. I'm Tommaso Di Fonso from the University of Padua, where I teach business statistics at the Department of Statistical Sciences. I'll be chairing the session, and I'm also the first presenter. We have 4 talks. 20 minutes are strictly allocated to each. If the presentation will take less than 20 minutes, we will have time for 1 or 2 questions. In any case, please use the chat or question answers window to make questions to the presenters so they take note of it and answer when they have time. As you know, this year, 3 student prizes are available for the Best Student Presentation Award. The 3rd and 4th presentations of these sessions, this session will be by PhD students, Candrica Pritularga and Niccolò Bertani, respectively. Participants at the session are kindly invited to rate their presentation. I will remind you before the starting of these 2 presentations. Thanks. So, well, let's start. In my talk, I show the results of a joint work with Daniele Girilumetto, a PhD student of the Department of Statistical Sciences of the University of Padua. We speak about hierarchical forecasting and forecast reconciliation, starting from the seminal paper by Professor Hindman and other researchers published in 2011. Several contributions have been presented up to now. In general, we may say that these contributions look for methods which are statistically well-grounded, feasible in view of practical implementation, and effective as for the quality of the results in real-world applications. In this spirit, in this talk, I focus on non-negative cross-temporal forecast reconciliation, which is a post-forecasting process aimed to improve the quality of incoherent base forecasts of a linearly constrained multiple time series by simultaneously exploiting both cross-sectional and temporal constraints while assuring both cross-sectional and temporal coherency and possibly non-negativity of the final reconciled forecasts. The main contributions shown today are basically 3 new results: the closed form expression of the optimal combination in least square sense point forecasts which fulfill both contemporaneous and temporal constraints, an iterative cross-temporal forecast reconciliation procedure which extends the 2-step procedure by Kourentzes and Athanasopoulos, and methodological and technical details on these 2 results are available in the draft paper on arXiv. The 3rd result is a new R package for ECO, performing cross-sectional, temporal, and cross-temporal point forecast reconciliation. The draft paper on arXiv contains an empirical application different from the one considered today, which is a new application on an old, well-known to forecast reconciliation people dataset. I consider a rolling forecast experiment on the Australian tourism demand monthly time series visitors night, classified as geographical divisions, Australian geographical division in states, zones, and regions, and by 4 categories of purpose of travel. In the end, the dataset consists in 525 unique time series. I stress unique time series, no redundancy in the time series. 304 time series are bottom level series, that is the most disaggregated one, regions by purpose of travel, and 221 series are upper level aggregated time series. These are the points of the presentation I will go through, starting with a very brief description of cross-sectional and temporal linearly constrained multiple time series, which are involved by many forecasting applications, not only in the standard or pure hierarchical or grouped form, like the one described in the left side of the slide, where we have a standard hierarchy. Here you have the matrix expression of the structural representation of this hierarchy. Please note that the summing matrix S has an identity matrix on the bottom and what I call cross-sectional aggregation matrix. In this case is the matrix, the first 3 rows in the top part of this matrix. On the left side, there is a more general linearly constrained time series where the top level series can be obtained either by linear combination of the variables on the left side or by linear combination of the variable on the right side. In this case, the linear relationships linking all the variables can be expressed as zero constraints representation, but what is important to stress is that these are equivalent representations. But linearly constrained multiple time series are also those obtained when one variable is considered at different time granularities, as in for temporal hierarchies. Here we have a classical representation of the temporal hierarchies for monthly time series. Well, the idea is to combine the cross-sectional relationships valid for all the variables at the same time with the linear relationships that can be defined for each single variable observed at different time granularities. Here you have a toy example with a very simple cross-sectional hierarchy, one top-level variable and 2 bottom level variable of quarterly time series, and 2 equivalent representation from the cross-sectional point of view and from the temporal point of view. Please note that this superscript number in square brackets denotes the order of temporal aggregation. So 1 means that no temporal aggregation is in order, 2 means that 2 consecutive values are temporally aggregated. In this case, we are working with the example with the quarterly time series. The 2 quarterly temporal aggregates means semi-annual and so annual. Well, a sensible idea would seem to simply generalize the structural representation valid for one-dimension coherency, but we agree with the statement reported here by Kourentzes and Athanasopoulos that this task is non-trivial and computational demanding because of dimensionality and non-unique mapping. It's rather easy to figure out the cross-temporal structural representation of the toy example so far, and we have made in the slide, but in general, the large and sparse cross-temporal summing matrix is not easy to make explicit. So we suggest to consider a cross-temporal zero constraint matrix, H transpose, which is full row rank, which means that it has no redundant rows and does not pose any matrix singularity issues when used in the standard point forecast reconciliation formula, as I will show in the next slide. The constraints are expressed by using the vectorized, if you prefer, the stacked vector of the matrix containing all the temporal aggregated versions of all variables of the original cross-sectional linearly constrained time series. Well, as compared to the cross-temporal summing matrix, matrix H transpose is large and sparse as well, but in the draft paper on arXiv, we shows that it is rather easy to compute as a function of the cross-sectional aggregation matrix and of the highest time frequency. This simplicity comes from the fact that usually the cross-sectional aggregation matrix is the same at any time index and for any temporal aggregation order. By exploiting this result, the derivation of the cross-temporal reconciled point forecasts according to the optimal combination approach is rather straightforward. Well, as usual, we call y hat the incoherent base forecasts and y tilde the cross-temporally reconciled vector, which can be obtained as the solution to a linearly constrained quadratic minimization problem the important role here is played by matrix W. Well, we want that this matrix is positive definite. The solution is the projection of the base forecasts onto the linear subspace defined by the linear constraints, and this is the projection matrix. And if W is interpreted as the covariance matrix of the base forecasts, we have a simple expression for the covariance matrix of the reconciled estimates. Well, for the time being, the state-of-the-art cross-temporal forecast reconciliation technique, well, in my mind, is the only cross-temporal reconciliation technique up to now, is the very effective procedure proposed by Kourentzes and Athanasopoulos, which basically consists in 2 steps, where one-dimensional forecast reconciliation procedure is applied. In the first step, through cross-temporal, through temporal hierarchies. In the second step, through cross-sectional hierarchies. The final cross-temporally reconciled estimates are found by linear combination of the outputs of the first 2 steps. In the draft paper on arXiv, we discuss some possible weaknesses that we think are embedded in this procedure, but one of which we want to consider now is the fact that, well, we were not able to deal with possible non-negativity constraints in this framework. So we propose to build on the procedure by Kourentzes and Athanasopoulos by transforming it in iterative way by alternating forecast reconciliation along one single dimension until a convergence criterion is met. Well, in practical application, we have considered no problem of convergence were found. What is important and interesting is that in this framework, it is easy to deal with possible non-negativity constraints. We put all the results found so far, and something else not shown today, in the R package for ECO, which can be used to derive cross-sectional, temporal, and cross-temporal, this is new, reconciled forecasts from base forecasts made available by the user. As for the non-negativity constraints, FORECO makes use of the R package OSQP, which is very effective in solving large and sparse quadratic programming problems with the alternating direction method of multipliers. We made some first experiments to benchmark the package. When compared with HTS, which waiting for the complete Fable implementation of the reconciliate function may be considered today as the state-of-the-art R package for cross-sectional forecast reconciliation with possible non-negativity constraints, well, FORECO shows significant reductions in computation time, always larger than 20%, up to around 80%. Passing to the forecasting experiment on the Australian tourism demand dataset, we perform a rolling forecast experiment with expanding window, monthly steps, 85 forecast origins, and at each forecast origins, we compute 12 step ahead forecasts. We compute base forecasts by using automatic exponential smoothing by means of the R package forecast on log transformed data, following the suggestions made by Vikrasamuria, Tarlach, and Heinemann in the paper on statistics and computing published this year. What is important is that for each training set, we did the same for any temporal aggregation order and considered the right number of forecasts, 12 monthly forecasts, so 6 bi-monthly forecasts up to 1 12 months aggregates forecasts. The base forecasts are reconciled by using 3 unidimensional procedure. CS stands for cross-sectional. This is minimum trace cross-sectional reconciliation with shrunk covariance matrix. Obviously, no temporal coherence is fulfilled. 2, forecast reconciliation through temporal hierarchies. In this case, no cross-sectional coherence is fulfilled. The cross-temporal bottom-up counterpart of these 3 procedure. The cross-temporal is performed on the high-frequency forecasts, monthly forecasts, of the 304 bottom time series. Okay, is a very simple cross-temporal bottom-up forecast reconciliation. Then we consider the standard procedure by Kourentzes and Athanasopoulos, remind that non-negativity is not applicable, and its iterative variant. And finally, we consider three optimal combination cross-temporal forecast reconciliation by using very simple generalizations of the covariance matrix using unidimensional forecast reconciliation. Well, I want to take a look at the optimal cross-temporal block diagonal shrunk cross-covariance matrix, which in our opinion should represent a sort of generalization of the solution proposed by the minimum trace cross-sectional forecast reconciliation procedures. Obviously, we are using the in-sample residual of all the models computed for all the temporal aggregation orders for the variable. The WSHR is a shrinked matrix starting from the sample covariance matrix at any temporal aggregation order with the lambda shrinking coefficient. A multiple comparison has been performed across all series and forecast horizons for the procedures. We report the results obtained by using the average relative mean square error across all series and forecast horizons. Here you can see a heat map of the rankings, but what is more interesting is these general results. In our application, the iterative variance of Kourentzes and Athanasopoulos and the optimal cross-temporal combination with non-negativity constraints improve on base and one-dimensional reconciled forecasts and on simple and state-of-the-art cross-temporally reconciled forecasts as well. What is important is this improvement is clearly seen if we consider the monthly forecasts. The label on the x-axis denotes the cross-temporal procedure. Obviously, on the left we have the base forecasts, and the one line is the threshold line. All the reconciled forecasts improve on the base forecast, but the optimal cross-temporal block diagonal shrink and the iterative variant of Kourentzes and Athanasopoulos seem to perform better. Please note that the white background means that the procedure are completely in line with the prescribed constraints, non-negativity and cross-temporal aggregation constraints. The cross-sectional minimum trace obviously is not in line with the temporal constraints. The temporal, in this case, are not in line with the cross-sectional constraints, and here the Kourentzes and Athanasopoulos is not in line with the non-negativity prescripts. There are some negativity forecasts. Well, I think that this is enough for the presentation. I want to go to the conclusions. Cross-temporal point forecast reconciliations, in our view, seems to be a promising topic worth considering for future research. There are many topics we are working on and many ideas. We want to signal to you our research in looking for more realistic and hopefully effective approximation of the matrix W, and extending this cross-temporal framework to reconciliation of probabilistic forecasts and for dealing with intermittent demand forecasts with related non-negativity issues. So thank you for your attention, and I will be happy to discuss with you and to answer to any question you have. Thanks. So now I change the position, and there are 2 minutes for possible questions, and so if there are any questions. No questions
If no one's going to ask a question, I will, Tommy. Thank you very much for your talk.
Oh, yeah, Rob.
This is Rob Hyman speaking. Really interesting work, and I'm pretty impressed with your speed improvements. Can you comment on how you did that? Because Shanika spent quite a lot of time trying to find variations on quadratic program that exploited the particular problem to get this thing running fast, and yet you've made it run much faster. So I'm interested in how.
Sorry, Rob, I completely lost the last part of your question. Is about the speed time of the non-negative procedure?
Yeah.
Is it?
How do you make it go so fast?
Yeah, well, we have some details on it. Anyway, we simply tried several tools made available in R, and OSQP seemed to be really very performing in dealing with sparse quadratic programming and large quadratic programming problems. Well, we think it's simply this, and I'm not an operation research expert, so it's just what we can think. You know, I was working with MATLAB in past times, and optimizing procedures for sparse problems are generally quicker than all the other tools.
Have you tried any really big hierarchies? Because that's where we found issues. Our algorithm was chosen because it worked when you've got thousands of series, and some of the others might look good on small hierarchies but don't work well on big ones.
Okay, I just a minute to share my screen, coming back here, and well, if non-negativity constraints, no. For echo, just, okay. This is the replication of the experiment made in your paper in statistics and computing. So here we have a very, very large hierarchy, 1 million series. Obviously, we are speaking about cross-sectional hierarchy, and we have 158 seconds versus 324 seconds for HTS, which is, well, we think a significant improvement, and probably this is not the largest hierarchy we can consider, but it seems rather...
That's very impressive, Tommy. Well done. Good work.
Okay, thanks. Okay, I think we can go forward. So next presentation is by Mahdi Abolghazemi, postdoctoral research fellow at the Department of Data Science and Artificial Intelligence, Monash University, with the paper Forecasting Hierarchical Time Series with Machine Learning Methods. Mahdi?
Thanks so much for the introduction. Let me just share my screen. So can you see my screen?
Yes.
Okay, great. All right. Good morning, good afternoon, and good evening, whichever time zone that you are in. My name is Matthew, and today I'm going to present some of the work that I have done during my postdoc and a series of work in time series hierarchical forecasting with machine learning models. And I'm going to present just part of it in this presentation. So here is an overview of my talk. I'm just going to talk a little bit about supply chain problem that I got introduced to. And then I will talk a little bit about hierarchical forecasting and then some of the advances with machine learning models. So I got to know hierarchical forecasting during my PhD when I was working on my thesis, and I was working in a food, working on the data sets for a food manufacturing company in Australia. So actually the problem from a supply chain perspective, it wasn't just about developing models and developing the statistical model or machine learning models for that. It was more about the decision making that they can actually use hierarchical forecasting for it. So they wanted to make some decisions in top levels, some strategic decisions, and also they wanted to make some decisions in different levels of it, bottom level and middle level for other operational purposes. So just talking a little bit about this industry problem. It's a food manufacturing company in Australia. If you think about it, talking from a manufacturer point of view, they have two main retailers in Australia, and each of these retailers, they have distribution centers in different states in Australia. So 6 states for the first retailer, and then 6 distribution center for 6 states for the other distribution for the other retailer. So they actually, it's kind of interesting, the data sets that they have, because looking at their data sets, they are highly impacted by promotion. So it's actually a coordinated supply chain, and the products are highly impacted by promotion. So if you look at this a specific example that shows the total sales, the one on the top, it shows the total sales for one specific product over 120 weeks. The one in the middle, it shows sales for 2 retailers, 2 main retailers, and then the one in the bottom shows sales for all other for 12 states all over Australia. So it's interesting because if you look at the spikes that you see, all these spikes that you see, they are caused by promotion. And these spikes actually are happening at the same time. So for each of these retailers, so suppose retailer A has promotion, that means all distribution centers down here and all the shops, that would be like thousands of shops, they all have promotion happening at the same time. So the spikes are happening at the same time, but they never happen at the same time for retailer, but it is totally different story for retailer B. So when retailer A has a promotion, they never have this promotion, retailer B, and vice versa. So it's a coordinated supply chain, and the data sets are highly impacted by promotion. So they were actually interested in they were interested in predicting sales over promotional times, how it looks like in their hierarchy. So if you think about this hierarchy specifically, just for one of the retailers, they not only have different spikes over the time, but also the spikes for one specific distribution center, and the parent nodes for a retailer changes over the time. So what I mean by that is there are actually 6 distribution centers, as you can see in here. The size of the spikes for distribution A1, DCA1, is totally different from the DCA2, and they have a totally different behavior. Obviously, for example, if you think of New South Wales and Tasmania, we have a bigger state, and the spikes experience much larger elasticity and much larger jump than the jumps or spikes that we can see in other states. So if you look at this slide in here, it is evident what I mean. For example, if you look at DCA4, you can see that the distribution for promotional and non-promotional is very different in this distribution center. But for some other states, it's a little bit more similar. For example, you can see DCB2 and other states, as you can see. So the main problem was they were interested in finding the promotional sales, and then finding that how it actually evaluates through their hierarchy. So I got to read Rob's paper on hierarchical forecasting, and then I implemented some of the models that they had, bottom up, middle out, top down, TDFB. George, as George suggested, this model, and some other models, as you can see. If you look at here, this one shows sales for just one of the product, reconciled sales for just one of the product at the end, how it looks like. For example, if you look at this promotion time, you can see the actual one has shown in red. Still, there's actually a big difference between what they have, what the actual is, and what the reconciled forecast is at the end. So I thought about it, what we can do to reconcile this maybe better and find a solution to that. So I got to work on some machine learning models to directly forecast that with support vector machine and some XGBoost. I'm not going to talk about that one. It's on archive, and you can have a look on that paper if you want to see. But what I was interested in this one to see which one really works better on these data sets. Bottom up, optimal combination, middle out, top down, which one really works better for each specific product when you look at them. So then, this is, as you know, that there's a long debate going on in the literature, bottom up, what are the advantages and disadvantages of bottom-up model, top-down model, and the linear combination model, how they perform. So obviously, in many applications, often linear combination works better, but there are still scenarios and some cases that you can see bottom-up or top-down outperforms at different levels. So then we thought about it, what we can do. Can we actually use, use some sort of model selection? Can we have some sort of objective model to find out the best model that we can, the best reconciliation method that we can possibly use for the time series? So you all know that model selection has a long history in time series hierarchical time series forecasting in general. So it got introduced by Wright, probably one of the early papers that work on it. And there has been quite a few works in this area. And then again, if you think about time series features, that's again one thing that has been one main research area that has been suggested as a promising way to find out the appropriate model for forecasting hierarchical for forecasting time series. Then what we thought about, maybe we can combine these two and look at the hierarchical time series to see if we can use time series features to find out the best reconciliation model that we can use for reconciling hierarchical series. So we used TS features and extracted some features out of time series for all the series across all levels. And then we did some experiment that I'm going to talk about that. So I'm going to just pass over these mathematical notations. You all know about these mathematical notations, and Thomas also talked about that, top-down, linear combination, and yeah, so talk about this algorithm that we proposed. So talking about time series features and model selection, we propose this algorithm that we can, maybe we can use time series features to find out the best reconciliation method for the data sets in hand. So in this algorithm, so what we did, we simply create a train set and test set for our time series. And then we produce forecasting in a rolling origin fashion. And then for each, for forecasting on a rolling origin fashion, we find out what is the optimal, we reconcile with all different models, with top down, with bottom up, and with optimal combination. And we find out which one works better for those time series with those features that we have. We only applied, we only considered three reconciliation method: top down, bottom up, and optimal combination with shrinkage estimator. And the reason for that is because we wanted to have a diverse set of reconciliation models to see how they perform in our algorithm. So that's the first phase of the algorithm. And the second phase of the algorithm, what we do, we created a data sets for classification model. And then in the second phase, what we do, we look at the, we calculate the time series features for the test set. And then we put them all in a classification model. And then we ask classification model to predict what would be the best what would be the best reconciliation method that we can reconcile those time series with that method. So this flowchart probably is better than all those notes that I put in that algorithm. So visually and quickly reviewing that, what I mean is, so we split the time series in sample and evaluation set, and then we train and forecast time series on a rolling origin basis. We reconcile them with different HF hierarchical forecasting methods. And then we find out what is the best, calculate the accuracy for the reconciled forecast and find out what's the best method. At the same time, we are calculating the time series features on a rolling origin basis for this time series. We created classification model, and then what we want to do, and then we train this classification model. And then in the second phase, what we do, we calculate the time series features. And then here is the thing that I need to mention. For the time series features, obviously we calculate time series features for all series, but what we do, we take an average of the time series features at the bottom level, and then an average at the middle level, and at the top level, obviously it has only one, we only use the value of itself. And then we put all these features into a machine learning model, and we find out the top TS features that we have, the most important TS features that we have, and then we put them in a classification model, and then the classification models tells us what would be the best reconciliation method based on the TS, based on the time series features that we have. So just talking about the results. So what we did, we applied this on 55 set of identical hierarchical sales data. 55 data sets correspond to 55 products. We could not build a big hierarchy because with 55 products in it, because if we do so, then we have a really small set of data to train and evaluate, to train this model and build a training set for our classification model. So that's why we actually applied on one hierarchical series for one product, and that's across different locations. And then we apply that on 55 set of series, or 55 set of products that we have. So we forecasted with regression with ARIMA models, the base forecast, and we have got 120 weeks of data. We consider, I guess, the last 8 weeks, last 12 weeks as our test set, and then we've got the training set and evaluation set. We use XGBoost as a classification model. We tried SVM and random forest, but the results were not as good. So I'm just going to present the results with XGBoost model. So as you can see, the CHF shows the conditional hierarchical forecasting. It works pretty well, outperform other models in level 1, level 2, and an outside average. But at the top level, you can see that this algorithm hasn't been so as successful as the other levels. Both in terms of MACE and RMSSE, it shows promising results. And this is just a box plot of how it performs. You can see the only part that this is the box plot of the ratio, the relative accuracy of CHF to each of the models to optimal combination, bottom up and top down. As you can see, not only our model on average has done well, but also on single hierarchy also has done a good job. Except in that case that I talked about in top level in terms of RMSSE, it hasn't, a top-down model actually outperforms our algorithm. So I'm just mindful of time, a couple of minutes, so I just quickly run through this. Multiple comparison. Yeah, multiple comparison with BED.
Okay, couple of minutes, okay.
CHF model has significantly worked better than the other algorithms that you can see. And looking at the performance of the XGBoost model, you can see that for different classes in terms of precision and recall, you can see that our model has actually, it has done a pretty good job in terms of if you look at the precision and recall scores for bottom-up and optimal combination, but hasn't selected the top-down model very well. So that's the only part that has done actually that hasn't done a really good job, I would say. But final slide talking about the important features. So the algorithm choose nonlinearity at level 2, nonlinearity at level 1, and nonlinearity at level 0 as important features that, as you can see in here. And the reason is probably because we think the promotion has impacted cells, and it impacts the cells over a number of periods as well, and that caused a little bit of volatility in our time series and thus nonlinearity. A takeaway message: we can use time series features to choose the best reconciliation method, but that has to be done with some care about training the classification model and how we want to put these time series features. There are some other future works that we want to do, and papers are on archive if you would like to look at them. And thank you so much for your attention. I'm happy to take any questions if you have time.
Okay, thanks. Thanks, Madi. We have 1 minute for possible questions. Anyone?
Madi, one question, Madi. This is Nikos. I may have missed it in the presentation, but you're using the features to select between reconciliation methods or also between the forecasting models? Because you could easily do both, right?
Yes, we could do both, but we're only doing that for reconciliation method.
Okay, okay, thanks.
Okay, thanks, Madi. And so we can go to the next presentation. Kandrika, you can share the screen if you want. Kandrika?
Yeah, sure.
Okay, thanks. Well, the next presentation is Stochastic Coherence in Forecast Reconciliation by Kandrika Pritularga. Kandrika is a PhD student at the Center of Marketing Analytics and Forecasting of the Lancaster University in UK. This is a student presentation, so all participants of the session are kindly invited to rate this presentation at his end. Kandrika, it's up to you.
Thank you. So my name is Kandrika. I'm a PhD student in Lancaster University, and my supervisors are Ivan Svitunkov and Nicholas Korenis. So I will start with a brief hierarchical forecasting and then Wing-Tail reconciliation and its covariance matrices. So we develop a spectrum of the approximation, and we will explore the performance and also the uncertainty in Wing-Tail reconciliation, and we propose stochastic coherency, and I will conclude the talk. So as we know that forecasting is essential for supporting hierarchical decision, could be structured in order categories or time or combinations between those two. We can see hierarchical forecasting as an information silo for organization, because one unit and organization provide the forecast across a hierarchy. It may improve the flow of information. It may reduce the unnecessary cost depending on the characteristic of the organization. And the archaic method that we know today are the bottom-up and top-down, but both of them ignore some information in the hierarchies. But the current method, the state of the art in hierarchical forecasting, is called Wing-Tail reconciliation, proposed by Wickramasuriya et al. 2018. It reconciles all forecasts across the hierarchy with regard to a predefined linear constraint or hierarchy in this case. So just a brief about the Wing-Tail reconciliation. As we know from the previous talk before that, the Y tilde or the reconciled forecast is structured from these summation matrix. G here is a reconciliation matrix, and the base forecast, and base forecasts are produced from independent forecasting models. We know the Y hat here, but the question now is how to estimate G. And Wickamasuria et al. 2018 proposed to minimize the variance of reconciled focus errors subject to unbiasedness preserving property. So I mentioned this in the beginning of this presentation because we developed stochastic coherency from the unbiased preserving property. So the solution is shown like this. G is a function of S and W here is H step ahead base forecast error covariance and if it is difficult to estimate. And the literature provide W hat here as the approximation, or W hat here is the is estimated from the ensemble base forecast errors. Because it's coming from the ensemble base forecast errors, then it contains the estimation errors, and W hat here is uncertain. So if we have different sample sizes, if we have for different forecasting model, we have different W hat and we have different G hat. And notice that we distinguish between G and G hat here. So G here is the function of WH, and G hat here is the function of W hat. And the claim from the literature is that the mintage ring improved the forecast accuracy significantly, but in some cases, WLS works well. In this paper, in the top level of the hierarchy, WLS works really well. So how can we deal with that? And then we come up with the spectrum. So we start from the simplest covariance matrix, which is the OLS, and then it carries forward to the mintage ring and mintage sample. So what we are doing here is to order the covariance matrix based on the non-zero of diagonals, and we will see on in the result of this study that the choice of the covariance matrix will affect the performance of interreconciliation. So let's talk about the performance and its uncertainty. So we conducted a small experiment with I think 7 time series in the hierarchy and 4 bottom level. And we have the TGP of AR1, we apply it as AAN. So we have misspecified model basically. And we conducted interreconciliation for 1,000 times. So we have 8 covariance matrices as we saw before. So from the 1,000 times iteration, on average, interreconciliation works really well, undoubtedly. And this is we use the error measure of relative total squared errors here. And what happened? So we don't stop here. So we are interested in the distribution of from the 1,000 times iteration. So let's see what happened next. And in some cases, the interreconciliation doesn't work well. So we see most of the cases it works really well, but in some cases it doesn't work well because reconciled forecasts are less accurate than base forecasts. So remember that in this case we have a misspecified model in the beginning. So we are interested to see the performance of interreconciliation for different level of specification. So what happens if we have a different model specification? So this is our experiment setting. Again, we have 4 bottom level time series, 7 time series in the full hierarchy, and our GTP is R1, and the level of specification are R1 with non-parameters. It represents the perfectly specified model, automatic ARIMA selected. So we basically select the model in the same family of the model. And also we have ETS AAN, which represent misspecified model. And let's see the result from from the known forecasting models. There is no benefit or loss of doing reconciliation because the base forecast is basically equal to the reconciled forecast. And once we introduce uncertainty in the forecasting models, we see the gain. We will see the gain of doing reconciliation. So here, when we have the auto ARIMA and the GTP is AR1, and we basically introduce a small uncertainty in this case, we gain some accuracy on average, but we also observe some variability in error measures. So you can see that some of this part here shows that the mean reconciliation fails to produce more accurate forecast than the base forecast. But overall, basically on average, it was really well. So what happens if we have ETS-AAN? So we get more accuracy improvement compared to auto-ARIMA. You see that on average is about 91% here. But also we observe some variability as well. So there is some interesting finding here that we also notice some different performance from different covariant matrices. If we notice that here that we have WLS and mintage ring here, and the performance on average is quite similar, but the variability of the error measure are larger for mintage ring than WLS. So in general, we can say that the mean reconciliation improved the forecast accuracy on average at the cost of error measure variability. So it's not a free lunch, basically, depending on the modeling uncertainty. And also the choice of uncertainty in error measure depends on the choice of covariant approximation. And in this case, for example, for OLS here, it ensures that we have at least as accurate as base forecast, right? But for mean reconciliation, for example, here we on average yes, but in some cases no. So it works I think in expected value. So it connects to our spectrum before that the more we exploit information of the covariant matrix, the more accurate the reconciled forecast, but the more variable the error measure value. And based on this understanding, we come up with this framework. So we start from the modeling uncertainty here, and when we don't know the GDP, there is estimation errors, and then it fits to the base forecast uncertainty and fits to the forecast reconciliation uncertainty. On the other hand, we have to estimate G hat, and it is a function of S and W hat. And W hat here is coming from the base forecast errors, and the base forecast error contains the estimation errors from the ensemble. So basically, we see some uncertainty in the estimation of covariant matrix, and it fits to the reconciliation metric uncertainty. And we also face the selection uncertainty because it could be possible that a specific time series require a specific time series, but we don't know a priori. And we have to test whether OLS, such as scaling, WLS, mintage sample, mintage ring, which one works the best. So we have to test it before, and we suffer from selection uncertainty of the covariant matrix. And these two uncertainties accumulate the reconciliation method uncertainty, and it fits to the forecast reconciliation uncertainty. So we don't stop here that try to understand the sources of uncertainty in the reconciliation. So we try to see what is the main source of it. So we come up with the idea of stochastic coherency. Here, S is able to maintain, or the summation matrix is able to maintain coherency when the modeling uncertainty is almost zero. And we can see the empirical result from the experiments, and we can expand this sentence more in the next slide. And when we face modeling uncertainty, as a G hat to maintain coherency, while G hat is uncertain, and as G hat is conditional on information up to time t, so we define coherency from deterministic to stochastic. So we basically put expectation on G hat here, conditional to all information at time t, or we simply say S gamma is equal to S, and we maintain the characteristic of projection matrix in the population estimation level. Note here that you also notice that we differentiate between G hat, and gamma. G here is the function of S is the function of S and WH, and G hat here is the function of S and W hat. So they are different. So in order to demonstrate the concept, we try to decompose reconcile forecast error into several components. So using the assumption of projection matrix in SG, the reconcile forecast error here consists of irreducible errors and reconciled estimation errors. Suppose that we know the forecasting model are known, the parameters are known, then estimation error will be 0, and then the reconciled forecast is basically just irreducible error. And then it's the same as the base forecast. So this explains our finding in the when we know the GDP. But when we have AR1, for example, with estimated parameters, the estimation here is non-zero, not in the expected value. And now it depends on the quality of SG, how SG behave. So if it hits the target very well, then it may reduce the estimation error. But in some cases, it doesn't hit the target very well, and it may exaggerate the error so that the reconciled forecast error are less accurate than the base forecast. It depends because uncertainty of G hat here will determine the size. And based on this understanding, it basically changes the relationship between the sum squared base forecast errors and reconciled forecast errors. So in our paper, it is said that it could be possible, or it might be possible that the base forecast is more accurate than reconciled forecast, depending on the forecasting model and the choice of the covariance matrix. Even though on average, so the size here, the sign here is basically depending on the forecasting model and the choice of covariance matrix. In conclusion, we can say that uncertainty in forecast reconciliation originates from the base forecast uncertainty and reconciliation metric uncertainty, and it depends on the forecasting model and the choice of covariance matrix. And we shift the paradigm from deterministic to stochastic coherency, where coherency is subject to information at time t. This explains the uncertainty in the reconciliation, which has been overlooked by literature. So thank you for attention. I will welcome any question or any feedback. Yeah, if you like this presentation, just wait and move on. I will stop screen.
Thanks, Kandrika. We have time for 2 minutes for any questions. Any questions to Kandrika? Well, just a question from my side. In your presentation, I saw, but probably I was wrong, some similarities with the description of the geometric interpretation of forecast reconciliation shown yesterday and in a very recent paper, when it is said that the OLS is less variable, the OLS reconciliate forecasts are less variable than the other. Is in your view some links?
Yes, because I think we don't need to estimate the covariance matrix, so it basically reduces the potential uncertainty in the reconciliation. So it's only if we see the uncertainty of the reconciliation coming from the forecasting model and the uncertainty of reconciliation matrix, and in this case, the reconciliation matrix is fixed because we don't estimate the covariance matrix. Then it is an orthogonal projection, so it ensures that the projection is basically create a less shorter errors than the base forecast. Yeah, I think we have the same view on that.
But we are using an accuracy measure which is coherent with the loss function. If you use a different matrix, you could have different rankings between the methods.
So yeah, so we use the ME for mean errors for mean errors, and then we also observe the uncertainty. we also variability in error measure as well. But it doesn't really it doesn't show really well. It doesn't. The result is not really nice to present, I think. So we skip that. But we observe some uncertainty in error measures as well. So, but we haven't tried for different forecasting errors.
Okay, thanks. If there are no other questions, thanks, Kandrika, and we can go forward with the next presentation. Niccolò, you can, okay. So next presentation is by Niccolò Bertani, joint bottom-up method for hierarchical time series application to Australian tourism. Niccolò Bertani is a PhD candidate at INSEAD, France. Its main virtue is that it comes from the same town of myself, Padova. He is a student, a PhD student, so participants at the session are kindly invited to rate his presentation. Niccolò, it's up to you.
Grazie Tommaso. I would also say that the other virtue is that I graduated in the other university where you teach, in my hometown. So I hope you guys hear me fine. Well, thanks for the presentation and thanks for being here. I obviously hope you're all staying healthy and doing well. So today I'm going to be presenting this joint piece of work with Ville Satulpa and Shane Jensen. In this project, what we do is to propose a new method for hierarchical forecasting that models a large hierarchy using a fully probabilistic or Bayesian approach to develop a joint distribution over the hierarchy. More specifically, what we do in the paper can be summarized to the following. We start off by showing under general conditions that the bottom level series and their contemporaneous covariance can be sufficient for a joint model of the entire hierarchy. Based on this result, we go on and we construct this Bayesian model that only uses these sufficient elements that I've just mentioned. It also performs automatic variable selection across all lag terms of all the time series at the bottom level. And it produces both posterior predictive distributions for probabilistic forecasts, but also posterior distributions of the parameters, which allow us to have insightful inference in the, let's say, phenomenon that we're trying to study. So today, I'm going to be mostly focusing on the model and try to convey the highlights of the model, but I'm also going to touch upon the application, which is on the, I would even say, benchmark these days, Australian domestic tourism data. And I will try to get in the allocated time to the at least the point forecast accuracy results, but also hopefully discuss a bit about the way we can use the parameters and the posterior to do inference. So let me move on and present the highlights of the model. And let me start off by describing the formal grounding that we have for the model. So for deriving our formal grounding, we only need one mild, or at least I think it's a fairly mild assumption on how the data generating process behaves. And the assumption is the following. So every time t, bottom level observations, which I will denote by yt, are generated by some model mu plus additive error. So for a mu can be really sort of any model you can think about. There's no particular restriction of it. It can be non-linear, non-stationary. You can kind of think about what you want there. While for E, we have this with these three specifications, well, epsilon actually. It needs to be, the error needs to be zero mean, have contemporaneous covariance sigma, and have no dependency on previous errors, which means that basically there needs to be no lag dependence once we have specified our model mu. Okay, so if we agree on this assumption, then we can show the following. We can show that under this assumption and for a coherent model of the hierarchy, the bottom level series and the contemporaneous covariance matrix are sufficient for minimizing the squared errors of the entire hierarchy. And okay, well, this is a result. It's kind of a simplifying result to some extent because it says we can focus on just these two elements. But turns out that it's actually really not obvious how to take this result and map it to a modeling approach that we are kind of used to using, or well, this is kind of a repetition, but allow me that. And there are at least 3 reasons why this mapping is not that obvious. The first one is that in order to get a good estimate of the contemporaneous covariance matrix, we need to have model mu capture all the lag dependence across all time series. This means that for every time series, we need to consider its own past plus the past of all the other time series at the bottom level, because they could have some correlation with the present realizations of every time series. Obviously, this leads to very high dimensional models because the number of predictors grows quadratically in the number of bottom level series. And these models are highly likely to be non-identifiable because we don't even have enough observations for the number of parameters. Okay, this might be easily solvable because there's a fairly large literature on how to deal with high-dimensional data, or models, excuse me. But note that most popular approaches for high-dimensional data are actually univariate, so they wouldn't allow us to estimate that contemporaneous covariance matrix. For instance, think about the lasso. Because of these limitations, and actually to address these limitations, we introduced a new model, which we call the joint model map. And it's based on a Bayesian base model that requires 2 additional assumptions. The first assumption is that the model mu is a linear model of all the self and cross lags multiplied by the usual sort of linear coefficients, which we denote beta here. And the second additional assumption, so the third assumption so far, is that errors are normally distributed. And here the assumptions from 1 are kicking in, where we have 0 mean and contemporaneous covariance sigma. Based on these 3 assumptions, what we're going to be, the likelihood of our observations is just multivariate normal with the mean given by these, the product of all the possible cross and self lags, and the contemporaneous covariance matrix sigma. Now, this is still very highly, let's say, over-parameterized to some extent, because that vector X can be very large, have a lot of elements. And so what we're going to be doing is we still deal with that very large vector of possible regressors, but we're going to be inducing adaptive shrinkage on the betas in order to select only the best ones and reduce the other betas to be irrelevant for forecasting. How are we going to be doing that? We're going to be using what are known as spike and slab priors. So in particular, we're going to be using absolutely continuous spike and slab priors. And to each beta, subscript P, in order to indicate each beta for each predictor, we're going to be defining that as being possibly drawn for one of 2 priors, normal priors. And we're going to determine which one of these 2 priors to assign the beta to based on the data. These priors look as follows. So in one case, beta will be attributed, let's say, the blue prior, which is a vaguely informative prior, which is going to allow beta to take large values in the posterior, in its posterior. If the data tells us that that coefficient should not be in the regression model, or it's very, it's kind of irrelevant for the regression model, the beta is going to be attributed to the red prior, which is a very strongly informative prior around 0, which will induce a very small posterior value for beta, effectively kind of nullifying its role in the model. Now, this allows us to well, reduce the complexity of this model, but it's only performing shrinkage and it's not inducing sparsity. So we might still run into computational trouble with this model because we're still considering the full size of this vector cross and self regressors. So what we do is that we complement this base model with a filtering step for very high dimensional settings. And this filtering step is basically derived from the SpecensLab private formulation, and it will perform forward selection of the best regressors to introduce in our model. I'm gonna spare you the details in the interest of time, but basically this filter will select the best K user-specified K predictors for each bottom level series. We show in the paper that it satisfies the sure screening property, which means that for large enough K, the true model is going to be filtered with high probability. And once we have filtered this subset of optimal covariates, we will feed that into the base model that I've just presented in order to have the joint estimation with the contemporaneous covariance and to perform further regularization if it's needed. Okay, I'm actually doing pretty good on time, so let's jump into the application. Well, the data is going to be the Australian domestic tourism data that you're probably all familiar with. And we're going to be testing for the forecast accuracy based on 1 for 12 step ahead forecast, training on 96 observations. Now, for our method and model, we're going to be considering as possible predictors of every bottom level series up to 12 lags of every bottom series. This means that overall, our joint model has dimension of more than 1 million, which is absolutely not something we can estimate. So we do the filtering here, and we filter. We consider two options for filtering. We consider filtering just the 12 best predictors or the best 24, and we're still going to be estimating very highly dimensional joint models of size in the thousands. We're also going to use two specifications for the contemporaneous covariance matrix that induce different levels of shrinkage, and this is kind of to learn whether we need more or less shrinkage in the contemporaneous covariance matrix in this setting. We're going to be comparing the forecast results to the bottom-up method and the different variations of the reconciliation method. And here again, we're going to be considering, let's say, two specifications for each of these methods here. One that is, let's say, richer, tends to have more regressors, which is a 12-lag autoregression. And in the other case, we're just going to use ARIMA models automatically selected. Additionally, we will also compare our method to a simplified version of it, where we fix the contemporaneous covariance to be just diagonal and proportional to a scalar. I'm now going to move on and present only the point forecast results. In the graph that I'm going to be showing, I'm going to be using the simplified version of our model with only 12 filtered predictors as a benchmark to kind of give a sense of where everything is located. So this is what the results look like. Obviously, this is a nightmare to comment and in such a short time. So I just want to point out that the distributions of these points across the three forecast horizons are pretty similar. And I'm going to therefore just focus on the 1 step ahead forecast for commenting right now. So when we zoom in, that's what we can notice. Note that here at 1, we have this vertical bar that indicates what's the benchmark. Obviously, the benchmark relative to itself is always 1. And in blue, we have the different variations of our model, where the full dots represent the more sparse models and the hollow dots represent the less sparse. While the light blue represents less shrinkage in the prior for the covariance matrix. Here, instead, in respectively green, yellow, or red, we have the competing models. So I'm going to highlight only 3 things of this graph. Well, the first one is that we tend to improve in relative square error, since our different specifications of the model tend to lie on the left of this benchmark line compared to the alternatives which tend to lie to the right, with the exception of the MINT automatically selected models here for the regional level at one step ahead forecasts. And then I want to point out two things that I think are very interesting for hierarchical forecasting, and focus only on, let's say, the variations of our model, but they could also be noticed in the difference between the the automatically selected models and the 12-lag autoregression. And these two things are the following. Well, first note that, well, when we introduced the contemporaneous covariance, we actually got sizable improvements. Now, many of you will be familiar with the fact that when we introduced covariance matrix in a model, that could not lead to an improvement in performance or better fit. This is the case here, and in particular, the improvements in performance are larger as we go to higher levels of the hierarchy, and this can be sort of surprising if you think about the fact that ultimately we are modeling from the bottom. I think this is a pretty neat result. And the second result, which is probably my favorite here, is that if we compare, let's say, these two models, so a sparser model and a less sparse model, what can be noticed is that the sparser model performs better at the bottom, but the performance deteriorates as we move up the hierarchy, indicating that that model is too sparse to actually capture all the lag dependence in the data, and therefore it's giving a bad estimate of the contemporaneous covariance matrix. While if we use richer models, then the trend is basically the opposite. So the performance improves as we move up the hierarchy. And I think this suggests that for hierarchical forecasting, we might want to consider basically different standards of sparsity compared to problems where we're only interested in just, let's say, the most disaggregated level of the data. Okay, I'm actually doing better than I thought on time, so I'm just gonna briefly show this.
2 minutes, Niccolo. 2 minutes.
I have 2 minutes, okay. Then I don't have enough slides because I thought it would go long. I'm just gonna be showing a couple of results in the application. Now, we've said that our model takes all possible lags as possible predictors and just selects the ones that are most relevant for each time series. So it gives us a selection of for every regional level or aggregate, what other regions are predictive of that specific region, which is the graph you see on the left. So the arrows indicate that all those regions are predictive of Sydney, future tourism in Sydney. And on the flip side, you can see that we can also look at fixing one region. What is that region predictive of in the rest of the country? And so you have the complementary picture always for the region of Sydney. Now, this data is kind of suggestive of what can be the hidden dynamic, what is the hidden dynamics in the data, and can be used for instance, well, what we do in the paper is to kind of simulate how tourism propagates in the country, and see whether authorities would have incentives, for instance, to incentivize tourism more. Well, I'm gonna shut up here. Thank you all for listening. And there's a working, well, the current version of this paper is available on SSRN if you're interested. I'm happy to take questions. Thanks.
Okay, there is a question by Ross Olliman. Nicolò, you have time if you want to answer.
Sure, I see the chat.
Great presentation and very interesting model. Do you seasonally adjust the data before running the spike and slab autoregressive model?
No, we don't. It's
The data are
you have like yearly seasonality for instance, right? So that's gonna be just captured by the 12 lag, the 12 month back lag in our model here.
Yeah, just to conclude, I have a question, not a question, but an idea about you compare forecast reconciliation procedure with forecasting techniques. Your model is a forecasting model, while the other are reconciliation starting from very simple base forecasts. In my mind, the comparison would be fair if you use your model for temporary aggregated levels of the hierarchy, then reconciliate them and make the comparisons. We have discussed about this in the past. What do you think about?
So I think that we're motivating our model, and I think that was, excuse me, I am in the chat right now. The flow of why we come up with this model is kind of here. Based on this proposition where we're actually taking an objective function that is the entire hierarchy. So we have a hierarchical objective in our mind. We derive this proposition, and then in order to kind of make this proposition into a reality or an actionable model, we propose the model that I have described. So while ultimately it ends up being, let's say, a fancy bottom-up method, if you want, it's motivated by the fact that it minimizes errors across the entire hierarchy. And I think that's why I would consider that a hierarchical model.
Okay, thanks. We are only 2 minutes late, so well, I think that the session can stop now. I thanks the speakers and all participants. Well, I hope you will continue in enjoying the International Symposium on Forecasting. Thank you, and bye-bye.
Thank you.
Okay.
Thank you, Tommy.
Thank you, Tommy.
Oh, thank you to
Thank
you.
you, Tommy. Great work. All
Thank
presenters, thank you.
Hi, George. Thanks.
Ci colleghiamo al mio Zoom fra qualche minuto.
Fra qualche minuto. Io esco di qui. Ciao a tutti. Nicolò, ci sentiamo dopo.
Thanks, Tommy.
Take care. Thanks.
Okay. So,
Hi, Madi.
thank you so much.
Thank you so much.
If I end this meeting, I think everybody will be kicked out. So, yeah. Okay. Thank you so much. I'll see you in other sessions.